All right, well, this is going to be the complex one here. Let's see, what do I have? I have the system of 6, 4 on the left, 2 on the right springs attached to walls on either side, and some block here, and if we're oscillating, it would have some mass, but all we're looking for here is the effective spring constant, the effective spring stiffness of this thing. So you might remember, how did we do the effective spring stiffness previously? Well, we did something like this, right? We said if we had 2 springs, let's pretend they're both the same, K, on this mass, and we pulled it forward, then both of those springs would pull back at the same at sort of the same level. So because they both have the same spring constant, you'd end up with 2K. And similarly, if we had the springs arranged like this, K and K, then if I pull this guy over this way, this guy compresses by an amount delta x, while this guy extends by an amount delta x. And so again, this is 2K because this guy's going to be pushing, this guy's going to be pulling, both in the same direction. These guys here are both pushing back in the same direction. And for the final possibility, you have 2 springs connected end to end, like that. And then, if this guy gets pulled off at an amount x, and these two guys both have k there, this guy only gets pulled x over 2, and this guy gets pulled half as much as well, right? So because of that, the effective spring stiffness of this thing is actually half of a k, so it's k over 2. So those are sort of the elements for this problem, and that's what we talked about in the lecture a little bit. What this is going to be how to combine those to make things work. Now, basically what you have to do when you're doing this is you have to look at the parts, and you're more or less going to alternate, but what you need to do is you have to look at the parts to see what's going to happen. So, for example, these guys A and B over here, those two guys are sort of like one of those. And this guy here, all of the four on the left are like this guy over here. So we've got a sort of subsystem where if we take the effective spring stiffness of those two and the effective spring stiffness of those 4, we'll end up with a sort of simple way to do things. So what we're going to have to do is we're going to have to add the effective spring constants of both sides, the stiffnesses of both sides. So our effective spring constant is going to be k from the left-hand side plus k from the right-hand side. It's just like this, right? So this is the left-hand side, this is the right-hand side, left-hand side, right-hand side. So we just add the stiffnesses from both sides. And that's going to get us where we need to go. All right, so that seems all right to start with. If we look at the right-hand side, for example, or HS, right-hand side, there's no bar there. Here we have something that looks like this guy over here, right? This guy down here where you have the 2 in parallel. So because those are in parallel, the right-hand side is just going to be equal to Ka plus Kb, right, which is equal to 2 kilograms per second plus 1 kilogram per second, which is just 3 kilograms per second. That should be second squared, excuse me. Kilograms per second squared. So that gives us the value of Kr. So the effective spring stiffness on the right-hand side is 2 plus 1 is 3. Okay, that's nice and simple. That's sort of the easy side. So we've got the KR part. Then we need to get the KL part. So this part is KR. This part is KL. And now we have a problem because that's more complicated than one of these three things. So what we have to do is we have to break it up into parts and do each part itself. So sort of the first thing we do is we have to say, well, the left-hand side is in series. So that is going to mean that 1 over KL is equal to 1 over K4 plus 1 over K, I don't know, LR, because this guy's KLR, because it's the right-hand side of the left-hand side. Got to use some notation, even if it doesn't always look fun. So this isn't going to be too bad. This guy's easy, right? We just have a number, 1.5 kilograms per second squared for him. This guy, he's a little more complicated. Right? He's a little more complicated. That happens, right? Some people are more complicated. Some spring systems are more complicated. That's just the way they are. So let's go ahead and look at that part. All right. So we say the left-hand side is in series. And then if we look at just this, we look at this as a whole, it's in parallel, right? So that means this KLR that we're looking for is going to be equal to K3 plus this thing on the top. I don't remember what I said. Let's call it KS. So these two guys are going to be in series. I'm going to call them KS. All right, so we'll have to find KS for the top because we don't know what that is, but we do know what's going on there. So you notice what I'm doing here is things that don't have interior dependencies. I'm doing those first, and then I'm doing things more and more towards the inside. So that's all we need for that part. Now we have to figure out this part. Well, these are in series, so that means that 1 over KS that we're looking for here is equal to 1 over 1 kilograms per second squared plus 1 over 1 kilograms per second squared. All right. And I'm sorry about this. You know, I stopped because somebody was doing their yard earlier this morning. I did my yard work. I did my workout. I took a nap. I came back, and then somebody started doing the yard work again. I don't understand. So, anyways, I have basically 1 plus 1 equals 2 seconds squared per kilogram, right? Because that's 1 over kilograms per second squared. Now I have to do something with that to find KS. Well, I have to just do 1 over 1 over KS is KS. So that means 1 over 2, or 1/2, is what we need here, and that's kilograms per second squared. And so that is KS. It's this guy. Right? Oh, there's a KS right there. So we're good with that. Next, we have to get to the next part. I don't know why they have to do this to me. All right, next I have to do the last part, which is sort of push this back in here, and then after I get that, I'll push that back in there. And after I get that, I'll throw everything up here. So now we're just going backwards with the stuff that we'd thought of earlier on. So I guess this is a little complicated, but it's not that complicated, I hope. Let's see, I said KS is, that should be 1/2. 1/2 kilograms per second squared plus 2.5 kilograms per second squared is equal to 3 kilograms per second squared. So that's good. We can live with that one. Oh, good. I changed it all over here. Why didn't I change it there? Well, that's life. Oh, and I guess I went ahead and I did all the math over there. So that's just more math, right? I took this guy, plugged it in here. I took this guy, plugged it in here. So that's 1 over 3 kilograms per second squared and 1 over 1/2 kilogram per second squared. So 1.5 is 3/2, right? So that 1 over 3/2 is equal to 2/3, which gets you this 2/3 here. And obviously 1 over 3 is 1/3. So I have 1/3 plus 2/3 is equal to 1. And then I have to flip it over because I've got, this is actually 1 over KL here. So I have to flip that over to get to KL. And so that's just 1. So 1 over 1 is 1. So we have 1 kilograms per second squared. So that comes back up here. So we have 1 kilogram per second squared plus whatever we had on the right, which is 3 kilograms per second squared. And that should end up equaling 4 kilograms per second squared. And that's how you do that there. So again, I mean, it's actually pretty easy here. If you draw these boxes, each box has to be inside the other box. That's the big deal, right? So I'll draw this big giant box, red box. That's our entire system that has this effective spring constant here. Then we have the two gray ones, which are the right-hand side and the left side in series, right? So those are both inside the red box. There's nothing that we need to do inside the right-hand side, but on the left-hand side we have this big blue box. That's this sub-problem in parallel, right? This guy and this guy are in parallel. And then there's another box in here, another part we have to figure out, and that is in series, so we have to do the 1 over whatever stuff. And we end up, finding our answer and shoving it into that thing. So we're looking at the big and breaking up into the small, and then after we found all of the small ones, we're plugging them back into the bigger ones until we get back to the answer. So we're sort of reducing and then expanding. And that's sort of the way you have to do these problems. And it'll also be the way you have to do the problems in physics too when you do these for both capacitors and resistors. For some reason, we love to do these capacitor and resistor networks. They'll be exactly the same as one of these spring networks. All right. Well, thanks for listening. And I will do another one of these lickety-split. All right. Bye now.